So in this video, we're going to take our study of sequences and series a little bit further. Now up to this point, we've looked at what we can do to calculate the next term in a sequence. So using the previous term, how do I determine what's going to happen next? And then I can use that to continue to look at the behaviour as I go on from term to term. Well, what we need to start thinking about is the long-term effects. So how is this going to affect our scenario, our situation, our environment long-term? What's going to eventually happen? So in that case, and to look at that, we're going to look at the limits of sequences. So that's what this video is going to focus on. Now, if we think back to our sequences and series that we've looked at always look like this form. un plus 1 equals a un plus b. Now, un plus 1 is our next term in our sequence. Un is the previous. So what this is telling me is the next term in our sequence is equal to something happening to the previous term, then something getting added on or subtracted afterwards. This always has an effect. Now, the key thing we need to look at in terms of determining if there's a limit is actually this part here, the coefficient of our un. Now, if we think about the size of un, if you think about when you're multiplying two numbers together, so if I've got one number and I multiply it by something else, and that number is bigger than 1, what's going to happen to the number I'm multiplying is it's going to get bigger. And if I keep going that way, it's going to get bigger and bigger and bigger and bigger. So what that means is that if the size of this number here is bigger than 1, what I'm multiplying is going to start to get bigger and bigger and bigger, and it's just going to keep continuing on that behavior. So what I'm able to say is if the size of A is bigger than 1, my sequence is going to keep going. So something like this is going to happen. It's going to keep going up and up and up and up and up and getting bigger. Or if A is negative and the size of it is bigger than 1, it's going to keep going down and down and down and down and down and getting more and more in the negative direction. This is what we call a divergent sequence. So it diverges, i.e. it doesn't have a set limit, it just skews off to infinity or negative infinity. So if the size of this coefficient of un is bigger than 1, it's going to diverge. Now the sign doesn't matter, it just determines whether it's going to shoot up or shoot down. So for example, this one here is if a is bigger than 1, and this one here is if a is less than negative 1. So it's just going to shoot off down that way. If we think about it another way, if we take half a number, so imagine we've got a number and we're halving it every single time, the number's going to get smaller and smaller and smaller and smaller and smaller. It's going to get closer to 0 every single time. And that's the case for this sort of thing as well. So if the size of our A is less than 1, what's going to happen is this is going to get smaller and smaller and smaller and get closer towards a single value. This is going to converge. So it's going to tend towards a limit. So if you look at this one, this set of numbers here, this sequence is getting closer and closer and closer to what could be a limit if we imagine we put a straight line going across here. And it will never ever cross that limit. Same idea with this one. We could put a straight line going across here, calling that our limit, and our sequence will never get below that limit there. For this one here, this is when A is between 0 and 1. And this one here is when A is between negative 1 and 0. This is a condition for a convergent or divergent series. Now, if it's divergent, we can't have a limit. It'll just shoot off to infinity. If it's convergent, we have to somehow come up with a way to calculate that limit. And that's what this formula across the page tells us. If I have a sequence, un plus 1 equals a un plus b of that form, and my a value is between negative 1 and 1, it has a limit. So if negative 1 is less than a is less than 1, a limit exists. Regardless of what other numbers are in here, a limit exists if a is between negative 1 and 1. And this formula here tells me how I can calculate that limit. So the limit is equal to b, so our second term here, divided by 1 minus a. That there tells me how to get the limit of my function. So you can imagine I've got maybe un plus 1 equals a half un plus 2. Now I know a limit exists for this one because that is a half. It's less than 1. So I can use these values to get the limit of that function. So imagine that. It's b over 1 minus a. A is the coefficient of un, and b is the constant at the end. So b in this case is 2. So it's going to be 2 over 1 minus at a. So in this case it's going to be 1 minus a half. And then it's just working it out. So in this case it'd be 2 divided by 1 minus a half is a half. 2 divided by a half is the same as 2 times 2, which is then 4. So the limit of that sequence is going to be 4. We're able to use it to determine a limit of a sequence in that way. And this is particularly useful for real-life scenario-based questions. So let's have a look at one of those. So imagine I've got a deer population in a forest and it's said to drop by 7.3% every single year. Each year, they're going to introduce 20 new deer to the forest to kind of try and counteract that and balance out the loss. And the initial population is 200. So two-part question for you. 1, how many deer will be in the forest after 3 years? And 2, what is the long-term effect on the population? So the first thing we have to do for part 1 is come up with a recurrence relation. So our un plus 1 equals AUN plus B. Well, the A comes from the percentage we've got left. So it's said to drop by 7.3% each year. So we know we've got 92.7% left at the end of each year. So A in this case is 0.927. And B is the extra we're bringing in every year, so B in this case is 20. So we know that UN plus 1 equals 0.927 UN plus 20. I know my initial one is 200, so I know U naught equals 200. And it's from there I can then use this to calculate it. So I know that I want after 3 years, so I want to calculate U1, U2, and U3. That'll tell me the population after 3 years. So for U1, it's 0.927 times 200 plus 20 at the end. If I do that, I get 205.4. Now I know it seems strange, 0.4 of a deer. Keep the decimal in there now until we get to our ultimate goal of 3 years. Then we can work it out from there and round it appropriately. Second one then is 0.927, and remember it's times the previous year. So in this case it's times 205.4, then plus the 20 again. So in this case it's 210.4058. That's what we get for that one. And then U3, our third year, the one we're ultimately after, 0.927 times this one here, so times the 210.4058 plus 20 on the end again. So extra 20 they're adding in each year. What this then gives me is 215.0461. Now, what this means is I now have to look at this and relate it back to the scenario. I can't have 0.461 of a deer. Just doesn't work. You can't have a certain part of a deer. A leg doesn't count. So what we have to do is make sure that this is rounded properly. So what this tells me is that after 3 years, I have 215 deers. Okay. After 3 years, I've got the 215. I don't have a full deer yet from this, so I ignore that part there. Okay. Now the second part is what is the long-term effect on the population. The way to think about this is what's going to happen to the population. What's the limit after a long time? Well, looking at recurrence relation, we know a limit exists because of this. Now, this is a key thing here. You have to state that you know that. You have to state that you know a limit exists. So we'd have to start by saying a limit exists since -1 is less than 0.927 is less than 1. You have to state this sort of comment, regardless of what the number is here. You have to tell them you understand why a limit exists and then calculate it. Don't just jump in with both feet and calculate it. You have to tell them it exists. You have to show that you know the theory. So in this case we do that, and we know the limit is equal to b over 1 minus a. Now remember, b is the bit at the end, a is the coefficient of our un. So in this case it's 20 over 1 minus 0.927. Plug that all into a calculator, and what you end up getting is 273.97 to 2 decimal places. That there is the ultimate population, but again we have to look at that and say, what does this mean? Now normally the 9 would let us round up the 3, but you can't round up part of a deer. Think of the scenario. If I gave you most of a deer and left a leg off, could you round that up and say you've got a full deer? No. So we've only got 273 full deer. So therefore 273 deer is the limit. I.e., we'll never have any more than 273 deer. That there tells us what we need to know. Now this is how we'd work through a limit question and how we'd work it out from there. We have to be able to do this, follow the steps through, and get a good answer for it. Now another thing we're able to do is use the limit and work back the way to find coefficients if we know something exists. So let's imagine I put the statement to you. The sequence is defined by the recurrence relation un plus 1 equals kun plus 2k. First term is just given by u0. If the limit is 27, what is k? So imagine I give you a scenario like this, and we want to know what k is. Well, we know what the limit of the function is 27, so we have to start thinking in terms of that. We know the limit is equal to b over 1 minus a. We can read off b and a from there. We know that a is k, and that b is equal to 2k. So we know the limit in this case is given by 2k divided by 1 minus k. But we also know that that equals 27. So we can set up a nice little equation to be able to solve. Now this sort of equation here, you should be able to do that from S2 type maths. So we then end up with 2k equals 27, bracket 1 minus k, multiply out the bracket, 2k equals 27 minus 27k, 29k equals 27, k equals 27 over 29. Now it might look like a bit of a wonky number, 27 over 29, that's not what you'd expect, but remember this value here for k, because it's the un coefficient and we know a limit exists, has to be less than 1. If we end up getting an answer for this that's more than 1, you'd have to go back and check your work, and you've done something wrong somewhere. It's good that we know it, that we get less than 1, because if we don't, we'd have to make sure of it. A limit exists, that has to be the case. So when we're working out something like this, we have to remember those things. We have to remember the condition for a limit, so a has to be between -1 and 1. We have to remember to state that if we are working a limit out. We have to be able to tell them we know a limit exists because of this condition. And we have to then be able to use the formula L equals b over 1 minus a to be able to calculate that by getting the a and the b correctly from our sequence's recurrence relation.